The most difficult sliding tile puzzle we've looked at has a solution that's 31 moves from the initial board position. So why might breadth first search not find the solution? If you imagine breadth first search, we have to maintain a list of open boards for every board position at a particular depth. If we assume that every state has 2 children, and that's not necessarily true, some have more, some have fewer, level n is 2 to the n states, so 31 moves down has a lot of boards, and we can't hold all of them in memory at the same time, so we'd probably have an out-of-memory exception. Let's think about depth first. Why might depth first not find a solution that's 31 moves away? If the solution is over here, but we start heading down the wrong path, we could spend a whole lot of time exploring parts of the tree that don't take us to the solution, because we have to explore the entire subtree underneath number 4 here before we'd ever go back and try and explore the entire subtree under number 3. So the solution to this is heuristic searches. In heuristic searches, you don't always go down, you don't always go across. Instead, you have a way of trying to evaluate how promising a board position looks, and you're going to let your search be guided along the way by how promising intermediate board positions appear. So just to remind us, this is what our kind of overall pseudocode looks like. I've renamed some of the lists. So open was what we used to call toVisit. Open is all the boards that are still open for us to explore. We've generated them, but we haven't checked them. Closed is all the boards that we have already checked. So we're saying as long as there are still open boards to explore, we're going to remove one of them from the list. Once we've removed it from the list, we'll add it to the closed board list because now we've checked it. We actually have to check it. We get its children, and then for each of the children, as long as it's not already checked or already in the boards to check, we'll add it to the boards to check. So that was sort of the general idea. Okay, so the big change we're going to make now is we're going to remove the most promising board from our list of open boards. And I know you're thinking, well, how do you decide the most promising board? The answer is you write one or more heuristic functions. So a heuristic is going to be a method that assigns a number that says how promising a particular board appears to be. Typically, it will try and estimate the number of moves to the goal state. But it doesn't try and do a good job estimating. It's important that a heuristic run fairly quickly. So it will usually give an easy-to-calculate underestimate of how many moves. I think an example will go a long way here. The most famous heuristic for the sliding tile puzzle is the Manhattan distance heuristic. The Manhattan distance heuristic, we relax one of the constraints. One of the constraints of the puzzle is tiles can't move on top of each other. If tiles could move on top of each other, then the puzzle would be easy. For example, we would just slide the 8 on top of the 5, on top of the 2, all the way down to its goal position. 1 would slide this way to its goal position, and so on. Here we're imagining that this is what the goal state looks like, which is a little bit different than the goal that I had us looking for. Okay, so the Manhattan distance heuristic says, let's imagine that one of the constraints doesn't exist. We're allowed to slide tiles on top of each other. Now let's add up the total number of moves we would need to get everything in position. So the 8 tile needs to move 4 squares, the 5 tile needs 2 squares, the 1 tile needs 3 squares, 3 is already where it should go, 6 is already where it should go, 2 is already where it should go. So you add all those up and you get a heuristic score of 9. Notice that 9 is the number of moves we'd need if we can move things directly to where they needed to be. We can't, so this is likely an underestimate of how far away the goal is from this position. But this still works really, really well as a heuristic. Okay, so let's pretend that we're going to use that heuristic. Every single board, we have a method that will let us evaluate that board and return a number. That's our estimate for how far away from the goal is it. So how do we choose the best open board from our list? Oh, by the way, we're not doing A star yet. We're going to do best first search, otherwise known as greedy search first, because A star builds on top of this. Okay, so how do we remove the most promising board? Well, obviously you could loop over all of the boards and do the like find the minimum pattern. We're trying to find the minimum because a small number is more promising than a large number. But that's going to be very, very slow if we have a large open list. So it would be much better if we just kept our open list already in sorted order. So yeah, here's the slow idea. Loop over the whole list. It's much faster if we insert new boards already in sorted order. So we're not doing a full insertion sort. It's more like we're doing one step of the insertion sort because we're already keeping our list in current order, in sorted order. All we're doing is we're trying to insert a couple of new states, but keep the list in sorted order. So you can sort of use part of insertion sort to do that. There are always, I don't want to prematurely optimize here necessarily, but there are always faster things you can do. So rather than think about this as insertion sort, you could first binary search to try and find the position you're trying to insert to. There are data structures that would support you doing that very, very quickly. I don't want to focus on those things. So let's focus on kind of the overall algorithm, and then we can optimize afterwards. Okay, so that's best first search. So I think what you should probably do is pause the video and try and implement that. Or you could watch the rest of the video, that's fine. But try and implement best first search as the very next thing that you try. Okay, so what's even better than best first search? So consider this situation. I've got a board position here that returns a heuristic of 10. So we think the goal is probably 10 away from this board. We have another board position down there that's 10 moves deep, and it's got a heuristic score of 9. So think about which of these two boards would best first search have us explore, and then which one would we actually, in reality, want to explore. So this one, we've already, this board is already 1 move deep, and the heuristic estimates that it'll be 10 more moves. So that's 11 total moves to get to the goal. This board has a better heuristic, so best first search or greedy search would explore this board first because it's got a better heuristic. The problem is greedy search didn't pay attention to how long it took to get to the board that had the good heuristic. So it's not paying attention to the total path length. So if you look at the total path length, actually this board would be a lot better because even though it's got a worse heuristic, it's less deep in the tree. So this one has a total path length of 10 plus the additional 9 is 19. So that's what A star does. A star doesn't just look at the most promising board. A star looks at the board that has the best overall path length. So it incorporates information about the total, the current depth of each board. So the way you actually implement it is very similar. You can keep your method for calculating heuristic, but make a new method that's going to be what we'll call its A-star score. And the A-star score is going to be the board's current depth plus whatever the heuristic returns for that board. And then everything else is the same. We insert boards in this list in the order, in ascending order by their scores, and then we always remove the most promising board from the list. Writing good heuristics is sort of an art. I think it's totally fine if you want to use ChatGPT or a general internet search to try and figure out what are good heuristics for whatever your puzzle happens to be, especially Sokoban. And it'll give you a description. And then choose the one that seems the easiest to implement first. You can have heuristics. Well, let's not get more complicated. Okay, the end. That's A star. Good luck, team.